Secondary valency decides geometry of the complex compound. As coordination number is 6, what can you tell about the geometry? Yes, it is having octahedral geometry. These hybridized orbitals are allowed to overlap with the ligand orbitals that can donate electron pairs for bonding. Primary valency is actually equal to the oxidation number. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with session 4 of the chapter Coordination Compounds. So in the last session, we have discussed about isomerism in coordination compounds, right? And in detail, we studied about stereoisomerism, the different types of stereoisomerism, right? Geometrical and optical, as well as the different types of structural isomerism also, and the various examples for that. So in today's session, we are going to study about the first theory of coordination compound, right? So we are going to study about different theories regarding coordination compounds. So the first theory will be Werner's theory of coordination compound, right? And the limitations of Werner's theory. Then we'll move on to the next one, that is valence bond theory, right? And the applications and limitations of that as well we'll be covering in the sessions, right? So two theories we are going to discuss. So Werner's theory is the one which we are going to begin now. So the main postulates of this theory, of course, from the name itself, you can say who proposed this theory. It is Werner, right? So that is why it is called as Werner's theory of coordination compounds, right? So the major thing that you have to be clear in this theory is that there are two types of valencies, okay? So the main postulates are the central metal atom or ion shows two type of valencies. So we have discussed about coordination compound that there is a central metal atom. Surround it, there will be ligands and counter ions will be also present. So all of this we have discussed. So talking about the central metal atom, the central metal atom can have two types of valencies. First one is primary valency and another one is secondary valency. Okay. So what is primary valency? Primary valency is actually equal to the oxidation number. Okay, oxidation number. So in the last session, we have already discussed in detail about how to calculate oxidation number, right? So once you have calculated the oxidation number, that exactly is equal to the primary valency of the central metal atom, right? Now what is secondary valency? Secondary valency is equal to the coordination number. Right, it is equal to the coordination number of the central metal atom, or the coordination number of the coordination compound is called as the secondary valency. Right, so we have already studied that as well, how to calculate coordination number. Right, if it is a monodentate ligand, whatever is the number of ligands, that will be exactly equal to the coordination number. For example, if we have K4, Fe, CN6. Okay, so which is the ligand here? It is cyano, right? Cn minus is the ligand here. And is it a monodentate ligand? Yes, it is a monodentate ligand. And how many of them are there? There are 6. So of course the coordination number here is 6. So this is how you have to calculate. Now for example, another example let us take COEN thrice plus. So this example we are taking. So what does EN stands for? It is ethane 1,2-diamine, right? So what do we know about ethane 1,2-diamine? It is a bidentate ligand, right? It is a bidentate ligand. So here 3 EN ligands are there and it is bidentate. So in that case, it is not 3, it is 3 into 2. That bidentate point also has to be considered here. So the coordination number will become this 3 into 2. That 2 is because it is a bidentate ligand. Okay. So if it is monodentate, it is exactly equal to the number of ligands itself. If it is bidentate, you have to multiply the number of ligands into 2. Okay. If it is hexadentate, the number of ligands into 6 you have to do. So I hope it is clear. So this is what it means by primary valency, which is equal to oxidation number. Secondary valency is equal to coordination number. Now let's move on to the details of primary valency and secondary valency. So primary valencies are ionizable. Okay, they are ionizable and are satisfied by negative ions. Okay, so it is satisfied by negative ions, they are ionizable and it is equal to oxidation number. The secondary valency is non-ionizable, okay, it is non-ionizable. It is equal to the coordination number of the central metal atom or ion. It is fixed for a metal. Secondary valencies are satisfied by negative ions or neutral molecules that are ligands. Now, why this is ionizable and non-ionizable? So, as you can see here, the primary valency is ionizable. So, how do you calculate oxidation number or primary valency? Yes, we have to check on to the counter ion, then we'll move on to the coordination sphere, and then we'll calculate the oxidation number based on whether your ligands and counter ions are anionic or cationic, right? So of course it includes both. In this example itself we can take, it includes both the counter ion and the coordination sphere. Using both we are going to calculate the oxidation number, right? So primary valency is ionizable because the counter ion also plays a role in that, right? But coming on to secondary valency, it is non-ionizable. Why it is non-ionizable? How can we calculate coordination number? That is your secondary valency. It only depends upon the number of ligands, right, which is present inside your coordination sphere. So that is why it is non-ionizable. We have already studied in the first session itself that this particular coordination sphere does not dissociate into its constituent ions, right? Only K4, that is your potassium, and the coordination sphere will separate, but whatever is present inside the coordination sphere will not dissociate, right? This we have already discussed. So that is why it is non-ionizable, right? Now the primary valency is non-directional. Secondary valency is directional. And ions or molecules attached to satisfy secondary valencies have characteristic spatial arrangements. Secondary valency decides geometry of the complex compound. So secondary valency means coordination number. If we know the coordination number, of course we can predict the geometry of the molecule. The coordination number is 4, it can be either tetrahedral or square planar. If it is 6, it is octahedral, right? So in that way, knowing the secondary valency, we can calculate the geometry of the molecule as well, of the coordination compound as well. So I hope it is clear what is primary valency and secondary valency. And the important point to remember is primary valency is ionizable, secondary is non-ionizable. Primary is non-directional, secondary is directional. Clear? And primary equals oxidation number, secondary valency equal coordination number. Now let's take an example here, CONH36Cl3. Okay, so compound is given to you, coordination compound is given, you have to calculate primary and secondary valency. What is the primary valency? It is equal to the oxidation number. So how do you calculate the oxidation number? It is -3 here, and the coordination sphere will get a plus charge, right? So cobalt, I don't know, I keep it as X. Ammonia, it is neutral, right? So I put it as 0, which is equal to 3. So X will be what it is, +3. So what is the oxidation number? That will be exactly equal to your primary valency. Now coming on to the secondary valency, which is equal to coordination number. Coordination number is what? Right. How many number of ligands are there, right? So how many ligands are there? There are 6 ligands. And of course, ammonia or amine is a monodentate ligand. So you just use that number 6 itself. So that is your coordination number, right? And as coordination number is 6, what can you tell about the geometry? Yes, it is having octahedral geometry. So this is how you have to calculate the primary valency, secondary valency, and the geometry of the molecule using Werner's theory. So I hope it is clear. So now moving on to the limitations of Werner's theory. So of course, this theory is not the final theory based on the coordination compounds. There is a valence bond theory as well as crystal field theory that we are going to discuss in detail. So there were some limitations for Werner's theory. A few elements have the property to form coordination compounds. It couldn't explain why only few elements had the property to form coordination compounds. Why is that was not been able to explain. The bonds in coordination compounds have directional properties. So just now we discussed directional properties are there, right? So regarding that, no explanation was given, right? And coordination compounds have characteristic magnetic and optical properties. So based on the coordination compounds and their oxidation number, we can calculate the magnetic property also, whether it is diamagnetic or paramagnetic, right? So regarding that also, there was no explanation given. So because of these reasons, the Werner's theory was discarded. Now came the next theory, which is very important, which we have to study, that is valence bond theory. Okay, so let's understand valence bond theory. The metal atom or ion under the influence of ligands can use its N-1d, Ns, Np or Ns, Np and d orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar, etc. So what does this mean? Okay, so we have already studied about hybridization in class 11, right? So that means the orbitals of almost equal energy, they undergo hybridization and form a set of hybrid orbitals which are having same geometry and same energy, right? So this is what is hybridization. So as told, the central metal atom, right? In coordination compound, there will be central metal atom, right? And the central metal atom can have free orbitals of n minus d, ns, np, or ns, np and d orbital, right? N minus 1 d or d orbital can be there, which is free in the central metal atom. Right. So what happens is these orbitals will undergo hybridization, and it will form equivalent number of hybrid orbitals which will have the same energy and the same geometry. So now these hybrid orbitals will form the bonds with the ligands, right? So and the ligands will be the ones which will be donating the electrons. So based on the hybridization, we can predict the geometry of the coordination compound. So that means that in class 11 also we have studied, if we know the hybridization, we can predict the geometry, right? So in the same way, if we know the hybridization, we can predict the geometry of the coordination compound. So these hybridized orbitals are allowed to overlap with the ligand orbitals that can donate electron pairs for bonding. Okay. So first the central metal atoms vacant orbitals, that can be ns, np, d orbitals, they will undergo hybridization and form hybrid orbitals, and these hybrid orbitals will overlap with the orbitals of the ligands, right? And which are the ones which will be donating these electrons, from where the electrons will be filled to this hybrid orbitals? It will be from the ligands, right? Okay. It is usually possible to predict the geometry of a complex from the knowledge of the magnetic behavior on the basis of valence bond theory. So in valence bond theory, using the hybridization, we can calculate or we can understand the geometry of the molecule. Other than that, we can also predict the magnetic behavior of the molecule. Okay, so let's understand in detail about that. If the coordination number is 4, right, there are two possibilities. Hybridization can be sp3 or dsp2. Right. So if it is sp3, it will be, the geometry will be tetrahedral. If it is dsp2, it is square planar. And if it is 5, coordination number, if it is 5, it is sp3d. Right. And the geometry is trigonal bipyramidal. If it is 6, two possibilities, again it is there, sp3d2 or d2sp3. In both the cases, the geometry will be octahedral itself. So this table is very, very important. Right. So for coordination number 4, sp3, it is tetrahedral. dsp2, it is square planar. 5, it is sp3d, it will be trigonal bipyramidal. 6 can be two possibilities, sp3d2, d2sp3. In both the cases, the geometry is octahedral. Okay. So in detail, let us see for different compounds how we can calculate the geometry and the magnetic behavior using the hybridization. So first we are going to discuss about this molecule or this coordination compound which is given here, CONH3 6 times 3 plus. So this is the coordination compound given to you. So using VBT, how we can predict the geometry and the hybridization and the magnetic behavior, we are going to see. Okay. So the oxidation state of cobalt ion is +3 and has electronic configuration 3d6. The hybridization scheme is as shown in the diagram. Okay. So for cobalt atom, okay, for cobalt atom, which is the central metal atom here, based on the central metal atom, we are discussing the hybridization, right? So central metal atom, of course, is cobalt here. So cobalt, before calculating the oxidation number of cobalt, that is in its ground state, what is electronic configuration of cobalt? It is argon 3d7 4s2. Now the atomic number of cobalt is 27. So it is argon 3d7 4s2. Okay. So this will be the electronic configuration. Now what we have to do is, we have to calculate the oxidation number of cobalt in this particular coordination compound, right? So as you can see here, this is neutral, amine is neutral, this is X. So X plus 0 will be equal to whatever is the charge here. So it is +3. So calculating oxidation number is simple in this case. Okay. So now what we have to do is, this electronic configuration which is written here, it is in the ground state. Now in which oxidation state is our cobalt in? It is in +3, right? So it is in +3 oxidation state. So in that case, what happens is, 2 electrons from the s orbital and 1 electron from the d orbital will be removed, right? 3 plus means what? 3 electrons are being lost, right? So 2 electrons will be lost from the s orbital and 1 from the d orbital. Hence in CO +3 state, what will be the electronic configuration? Argon 3d6. Right, from s orbital both the electrons are gone, which is represented here 3d6. The last electrons or the valence orbitals is what we are representing here, right? So the 3d6 is mentioned here, 1 2 3 4 5 and 6, right? Using Hund's rule, singly we have to fill it, then start pairing. Right, so this is 3d6 which is represented here. Now the 4s, 4p and 4d of the cobalt atom remains free, right? Only 3d6 is there, 4s2 already the electrons are gone, right? Now what happens is, once it is forming the compound, that means once to this cobalt the ligand is approaching, which is the ligand here, amine. The ligand amine is approaching. What happens is, as amine is a strong ligand, when it is approaching near the cobalt, what happens is, this electrons will start pairing up. So what happens? These two will pair up, these two will pair up. So what happens? Already 1, 2 are here, now 2 here and 2 here, it will be pairing up because your amine is a strong ligand, right? So what will happen now? You will get 1, 2, 3, 4, 5, 6. All of them are paired. Right, so I hope it is clear. Till there it is clear. So now what happens is, how many free orbitals is required to form this particular compound? See, as you can see here, it is CONH3 6 times, right? There are 6 ligands which is present, and the 6 ligands should form a bond with the central metal atom. So we need 6 free orbitals, right? Which are those? You can see here already this is being paired, and here itself these 2 d orbitals are free for us. So we take these 2d and this 1s, and we can take the 3 p orbitals here also. So in total, what will be the hybridization here then? Which are the free orbitals present? D2, that is 2 d orbitals, 1 s orbital, 3 p orbitals. So these orbitals will undergo hybridization and form what? Yes, D2 sp3 hybridization will be the one which is formed. So as it is 6 orbitals combining, it will form 6 hybrid orbitals, which is represented here. Now to the 6 hybrid orbitals, each of the amine will contribute 2 electrons, right? So now what happens? From here, one amine will be forming a bond, here one amine will be forming the bond. So from each of this nitrogen atom, 2 electrons will be donated. So here also one amine, here also one amine, here also one amine, and here also one amine. So this is how the according to valence bond theory, the coordination compound is being formed. Clear? Okay, so after the hybridization is happening, what happens? The amine will form the bond. Okay, so I hope it is clear. So in this case, as you can see here, this in d orbitals itself, they underwent pairing, right? The electrons underwent pairing, and here itself you got the free orbitals inside the d itself. That is why it is called as an inner orbital or low spin complex. Inner orbital complex. From the inner orbital itself, we are taking the 2d orbitals, right? So this is why it is called as inner d orbital, right? So it is an inner orbital or low spin complex. Another name is low spin complex, and the geometry is octahedral. Of course, coordination number is 6. So the geometry is octahedral. Now, regarding the magnetic property, it is diamagnetic because of the absence of unpaired electrons. So if all the electrons are paired, right, then the magnetic property will be diamagnetic. If at least one electron is unpaired, it will be paramagnetic. So as you can see here, in all the orbitals, electrons are paired. 2 electrons are present in each orbital, right? Hence the magnetic property is diamagnetic. Okay, so I hope this example is clear. Now let's move on to the next one, COF6 3-. Right, so let's follow the same steps and understand the magnetic property, whether it is low spin or high spin, whether it is inner orbital or outer orbital, all of that let us discuss. So again, what is the first thing we have to do? Identify the central metal atom. It is again cobalt. So what is the electronic configuration of cobalt in its ground state? It is again argon 3d7 4s2, right? Okay, now what we do? We have to calculate the oxidation number of cobalt in this particular coordination compound, right? So fluorine, of course, it is anionic, -1 charge is there. So 6 of them are there. So I put 6 plus 6 into -1 will be equal to -3, right? So 6 into -1 is -6. So x will be equal to +6 -3, which will again give me +3. So the oxidation number is again +3. So in the ground state, it is argon 3d7 4s2. So now in the +3 state, what will be the electronic configuration? It will be argon 3d6 again, right? 2 electrons from the s orbital is gone and 1 electron from the 3d will be gone. So it will be argon 3d6. Clear? So that is represented here 1, 2, 3, 4, 5, 6. Okay, 3d6 is represented here. 4s, 4p and 4d will remain free. Now what happens? In the previous case, what happened? As amine was a strong ligand, these electrons will start pairing up. But in this case, the ligand is different. It is fluorido. So in that case, fluorido, your chlorido, halogens are generally weak ligands. So as it is a weak ligand, what happens when the ligand is approaching the central metal atom? The pairing will not take place because it is a weak ligand. So what happens? The electrons will remain as it is. It will not pair up. Right? But how many free orbitals do we require? We require 6 free orbitals, right? So from here, of course, I can't take because it is singly occupied. It has not paired up also because the ligand is weak, right? So which are the 6 d orbitals now I have to consider? It is from 4s, 1 orbital, from 4p, 3p orbitals, and from 4d, I'll take 2 d orbitals, right? I need totally 6. So 1, 2, 3, 4, 5, 6 total. 6 has been considered. Now this 6 orbitals will undergo hybridization and form, yes, how many? 6 hybrid orbitals. And which is the hybridization here? It will be S and how many P? 3P and how many D? 2D, sp3, d2 will be the hybridization. I hope it is clear. It is sp3, d2. Now to this sp3, d2, 6 sp3, d2 hybrid orbitals, fluorido ligand will form the bond, right? So as you can see here, 2 from each fluorido ligand will be contributed to the central metal atom. So this is how the sp3d2 hybridization is coming, right? Now coming on to the geometry, we have already discussed if it is sp3d2 or d2sp3, it is octahedral geometry itself. Now coming on to whether it is inner orbital or outer orbital. In this case, we classified it as inner orbital complex because from the inner orbital, that is inner d itself, we are considering the 2 d orbitals. This is your outer d, that is 4d. We did not even consider the outer d. We took the 2 d orbitals from the inner d orbitals itself, which is 3d. We did not take from 4d, we took from the inner orbital itself. But in this case, from where did we consider the 2 d orbitals? It was from the outer d. That is not from 3d, it is from 4d, right? It is from 4d. That is why it is outer orbital complex or high spin complex. Clear? Now coming on to the magnetic property. Yes, can you say that it is diamagnetic? No, right? There are unpaired electrons which is present here. Hence it is paramagnetic. Hence it is paramagnetic. I hope it is clear. Now let's move on to the complexes having coordination number 4. So we have already discussed there are 2 possibilities, sp3 and dsp2. So both these we are going to discuss using one example, right? So first example, for a tetrahedral complex we are going to consider NiCl4 2-. Okay. So again, in the same steps we are going to follow, which is the central metal atom here, it is nickel, right? So for nickel, what is the atomic number? It is 28. So the electronic configuration is argon 3d8 4s2. Right. Now what do we have to do? Oxidation number of nickel we have to calculate. So for chlorido, it is -1. How many are there? 4 are there. So x plus 4 into -1 will be equal to -2. So it is x will be equal to 4 minus 2, which is equal to +2. So oxidation number is calculated. So now what happens in nickel in +2 state? What will be the electronic configuration? These 2 electrons will be removed, right? So it will just become argon 3d8, right? It's just argon 3d8. The 2 electrons is gone. Okay, so which is represented here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 3d8 is shown here. This is the 4s and 4p of the central metal atom, which is nickel. Right. Now what happens again to the central metal atom when the ligand is approaching? What happens when the ligand is approaching? Either it will pair up or it will not pair up. The electrons, it will pair up or not pair up based on the strength of the ligand. So as I have already discussed, Cl, which comes under halogens, it is a weak ligand. As it is a weak ligand, what happens? Will the electrons pair up? No, these electrons will not pair up. So the inner d orbital is not available. What we have to consider, the next available orbitals we have to consider. So what is the coordination number here? It is 4. So how many free orbitals do I require? I require 4. So I take this 1s and this 3p. So do I get a total of 4 orbitals? Yes. Now these 1s and 3p orbitals undergo hybridization. Which will be the hybridization? It will be sp3, right? So 4 sp3 hybrid orbitals will be formed, to which the chlorido ligands will form the bond by donating electrons, which is shown here. 2 electrons from each of the chlorido will be donated, right? So now what happens? Which is the hybridization? It is sp3. So if it is sp3, we know that the geometry of the molecule will be tetrahedral. The geometry is tetrahedral. Now moving on to whether it is paramagnetic or diamagnetic, you can observe here it is unpaired electrons are present. So of course it is paramagnetic in nature. It is paramagnetic. Now can you tell me whether it is inner orbital or outer orbital? Right, we have not considered orbitals from the inner shells. It is from 4s and 4p. So of course it is an outer orbital complex. So I hope that is clear. So it is an outer orbital complex or high spin complex. So I hope it is clear. Now one more possibility is there when the coordination number is 4, that is a square planar complex. So let's take the example of NiCN4 2-. Okay. So here also again in the ground state, what is the electronic configuration of nickel? It is 3d8 4s2. Argon 3d8 4s2. Again, if we calculate the oxidation number, it will be +2 itself. Right. It is -4 here and X here, which will be equal to -2. So this -4 goes to other side, it will become X is equal to +2 itself. So the oxidation number is still the same. So what happens in nickel 2+8? The electronic configuration will be argon 3d8. The 2 electrons will go from the 4s orbital. Right? I hope it is clear. Now what happens? That is represented here 1, 2, 3, 4, 5, 6, 7, 8. Right? Okay. Now to this nickel, which is the ligand present? It is cyano. So of course cyano is a strong ligand. So which are the strong ligands? Till now we have discussed amine is a strong ligand. Cyano is also a strong ligand. So the list of strong ligands we will be studying in the upcoming sessions, which comes under the next theory. In detail we are going to study here. Okay. So in this case also, what it is, halogens we have discussed, they are weak ligands. Cyano is a strong ligand. So what happens? I mentioned now it is a strong ligand means what will happen? Yes, the electrons will start pairing up. So what happens? These 2 electrons are unpaired. These 2 will pair up. So that pairing up is what you can see here. Right. Now, what is the coordination number? It is 4. So, how many orbitals do I require? I require 4 orbitals, right? So, the first orbital I can consider from here itself the inner d orbital, right? The next one is the s. And how many p do I require? 2 p's I require. So, totally 4 orbitals will undergo hybridization. Now, which will be the hybridization here? It will be d, right? This d is considered dsp2. D, S and 2p orbitals. So this is the hybridization, right? And to this hybrid orbitals, 4 hybrid orbitals, the cyano ligand will donate the electrons and form the coordinate bond. Clear? Right? So this is dsp2. So again coming back to the details, what will be the geometry of the coordination compound? It is dsp2. So the geometry will be square planar, right? The geometry is square planar. Now all the electrons are paired, right? There is no single unpaired electron. So of course it is diamagnetic, right? The magnetic behavior, it is diamagnetic. Now whether it is an inner orbital or outer orbital complex, we have considered the inner orbital itself, right? From the 3D, we have considered the first orbital, right? We didn't start from the outer, we have started from the inner itself. So, we have considered inner orbital. So, of course, it is an inner orbital or low spin complex. So, this is how you have to calculate and predict the magnetic behavior as well as the geometry using the hybridization of the central metal atom. So, I hope it is clear. VBT is completely clear for you. So, these 4 examples are very important. That is sp3d2, d2sp3, sp3 and dsp2. Okay, so I hope these 4 examples are clear for you. In the next session, we are going to study about the magnetic properties of coordination compounds as well as the next final theory, that is crystal field theory, as well as the limitations of valence bond theory we will be discussing. Okay, so I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.